Okay, all right. Well, let's see, it's 4:59 still, so we'll wait half a minute for the late attendees. All right, welcome everybody to session 6A about various algorithms for string matching, array distance, and related problems. So we have 4 great talks. Let's right away go into it. As usual, remember, if you have questions, please ask them into the Q&A. Feel free to include the name of the speaker to avoid ambiguity. All right, so let's move right away to the first talk about approximating text to pattern Hamming distances, and it's going to be given by Shai Golan.
So thank you very much. So this is joint work with Timothy Chan from Illinois University and Tomasz Kociumaka, Tzvi Koplovich, and Dali Porat from Bar Ilan. So in the paper, we consider the Hamming distance, where it's defined for 2 strings of the same length as the number of aligned positions where the 2 strings have different characters. In the text-to-pattern version of the problem, we want to compute the Hamming distance between the pattern and every substring of the text of length m. So we are given text and pattern, large text and small pattern. And we consider in the paper the version of approximate text-to-pattern Hamming distance, where we are given an approximation parameter epsilon, and instead of computing the exact Hamming distance between the pattern and every substring of the text of length m, we want to compute just 1 plus minus epsilon approximation for this value. So what is known about this problem? So the first algorithm consider this version of the problem is by Karlov from the 90s, and its running time is epsilon to the minus 2 n log squared n. Then Indic introduced an algorithm that improves the result for a decision version of the problem, but achieves slightly worse running time for the general problem. And recently, Koplovich and Porat achieves improvement in the epsilon dependency and breaks the epsilon to the minus 2 barrier and achieves epsilon to the minus 1 times n log squared n running time. And the common technique in all these algorithms was that they use alphabet projection from the large alphabet to some small alphabet using some randomization. And then compute several convolutions, and this was done by the FFT algorithm. And when we see this, we have 2 questions arise. The first is, can we break the barrier of n log squared n running time? Let's ignore the epsilon, assuming constant epsilon. And the second question is, can we avoid the FFT usage and still get something which will be near linear? And in the paper, we give positive answers for these 2 questions. And just in the very, very high level of idea, we show how to use sampling techniques together with fingerprints in order to break this barrier. In addition to the general or to the title of approximate text to pattern, we show that using the same technique, we can achieve many results in different versions of the problem. So for example, we can achieve truly linear time, which means that our dependence on n is just linear. This is done by bit packing tricks. And we also show that for the exact Hamming distance, not approximate, just we want the exact Hamming distance, but up to a threshold k, we can achieve a running time which improves upon the best algorithm known so far by Gorbaczovsky and Uznansky. It's done, we shave some log factors. We show that in the other hand, if we want to improve the epsilon dependence and not the logarithmic dependence on n, we can achieve linear time, O tilde of n time, n times polylog n for large patterns or small epsilon. The relation between the pattern and the pattern and the epsilon is considered. And we show also that we can achieve sublinear algorithms for large Ks, and also it leads to property tester that can decide whether, with high probability, whether there exists an exact match of pattern in a text, or all the substrings of the text of length m are far, which means here at least delta times m, far in the Hamming distance from the pattern. And finally, we also introduce streaming algorithm that where the text derives character by character, and we have a very small space. We can use just epsilon to the minus 3, O tilde of epsilon to the minus 3 space. Sorry, we can use epsilon to the minus 2 square root k or epsilon to the minus 1.5 square root m. It depends whether k is large or not, and achieve running time, which is O tilde of epsilon to the minus 3. And that's it.
Okay, thank you so much. So let's see if there are any questions. I don't see any questions yet. I guess the results are very clear. Let's see, let's wait a little bit. I guess I can ask a question. Are there any lower bounds in any of the settings, like property testing, like about the dependence on
So for
epsilon?
property testing, this is the first result for pattern matching, so I don't know about lower bounds. For streaming, there are the dependence on k, for example, it's in there is lower bound for the space usage. For the Hamming distance up to k, there is a conditional lower bound which was already for the previous result by Gorbaczovsky and Uznansky, but we shave just logs that it still don't. It's still okay with the lower bound.
So there is also a question from Q&A. Is there a connection to DTW distance?
What is DTW distance?
Okay, so maybe, yeah, I'm also not sure. So maybe the attendee can clarify dynamic time wrapping.
Sorry, but I'm not sure exactly what is it, so I believe not. But maybe there is some connection.
Warping, I guess. Oh, this is by Ryan Williams. Dynamic time warping. Okay, well, I guess it's maybe it's like later you can, if you find the connection, you can answer.
Yeah, I will.
Right. So I guess if you look, I mean, it's a lot of algorithms. Where do you see there is room for improvements? I guess they're nearly optimal. I guess linear time seems.
So there are some parts of where the actual, for example, in the beta epsilon dependence, the actual constancy is not optimized and could be improved even more. And I think that's it now.
I see, good. So we can, and you said, I guess you don't use FFT. So you mean because FFT?
In the main result, in some of the results here, you need FFT, but in the main result about approximating the Hamming distance, you don't need FFT.
This is advantage because you're saying FFT is only theoretically kind of fast, the constant is bad. So you're saying you have probably better constants, or is just simplicity?
Not necessarily. I think it's kind of interesting that all the previous results use this algebraic magic, and it's just to use some restricted settings and achieve another approach that also gives us many results. But I think from the theoretical perspective, it's also interesting to be more restricted.
All right, great. Excellent. So I guess, let's see. Well, perfect timing. So I guess, yeah, you can answer more questions, I guess, in Q&A. Feel free to ask more questions for Shai. I guess right now we'll move to, maybe you can stop sharing the screen. So we'll move to the, thank you so much. So yeah, we'll move to the second talk by Aviat Rubinstein. So Aviat is here. So the talk is, does preprocessing help in fast sequence comparisons? And Aviat will give it up.
Thanks. Hi, everyone. So this is a joint work with Elazar Goldenberg and Bar Nasaha. I'm very excited to tell you about this work, but I'm also a little sad today because this work would never have happened in an online without running into Elazar and Barna in a real physical conference. So I hope we get to see you all in person soon. Good. So our goal is to compute edit distance. In edit distance, we're giving two strings, x and y, and want to compute the minimal number of insertions, deletions, and substitutions that transform x to y. The favorite application of edit distance is bioinformatics, where we care about DNA sequences, and DNA sequences are really, really, really long. The other thing about DNA sequences is we have a lot of them. And whenever we have all these DNA sequences, we spend at least linear time constructing or reading or sequencing each of those strings. And then we want to make a lot of pairwise comparisons. Then we can construct the family tree of the cat, for example. Some very timely applications, some very important applications. Now, this is a joke. I don't think you can hear each other laughing on the Zoom, so I added a little sound effect. It was a great joke, yeah.
Okay, I liked it. It's good.
Thanks, Evgeny. So here's our model. There's going to be a pre-processing step where, Alice, the ocelot, is going to pre-process her own DNA sequence, and then Bob, the bobcat, is going to pre-process his own DNA sequence. And then in the query step, we have two strings together with the outputs of the pre-processings, and we want to compute edit distance. So this is the most important slide. This is the model. And once we have this model, we can ask, does a pre-processing step help? In general, the answer is no. So there is a folklorish theorem that, assuming strong exponential time hypothesis, you still need quadratic time, even if you had, say, n to the 100 pre-processing time. We also proved that, so the main open question is whether you can do a 1 plus delta approximation algorithm for edit distance in truly subquadratic time. So if you can do that with polynomial pre-processing, you could also do that without polynomial pre-processing. So that's all disappointing. Why am I still giving a talk about this stuff? So in some cases, we actually have much better algorithms. For example, we consider the special case where the edit distance is small, so the strings are only delta far apart in edit distance. And there we can do with near linear pre-processing time, which is basically free because we have to write the strings anyway, so that takes linear time. And then we have delta squared query time, which is tight, assuming strong exponential time hypothesis. Just for comparison, the state of the art in terms of sublinear time algorithms for edit distance was this algorithm from last Fox that gets a delta versus delta squared approximation. That's a very poor approximation. And the running time is something like delta cubed plus an n over delta term. We have some other algorithms. For example, permutation, LCS, this is a pre-processing analog of longest increasing subsequence. And here it's again a near linear pre-processing time. and the query time is improved from delta squared to order of delta, up to log factors. We have even more algorithms. So this algorithm 3 works for the general case where we're not making any assumptions about the strings. And here we get a 7 plus epsilon approximate edit distance algorithm. The pre-processing time is quadratic, like you would need to compute exact edit distance, but that's only the pre-processing. And the query time is roughly n to the 1.5. For comparison, the state of the art by Andoni runs in roughly the same running time, but the approximation factor is some huge constant but huge factor. Last result I wanted to say about is pre-processing only one string. So here our algorithm is slightly better than the state of the art for no pre-processing, but we still get some non-trivial saving with only pre-processing one string. Good. So just to recap, the main exciting thing about our paper is asking the right question. So it's this model where there's distributed pre-processing. Alice pre-processes her string, Bob pre-processes his string, and then we want to compute edit distance using this pre-processing. The worst case is still hard, but we get much better algorithms, and often and they're also much simpler algorithms. A couple of there are lots of future directions that would be great to take this. One example is better approximate edit distance with pre-processing only one string. It's a very natural question in terms of applications. And also making the query time for approximate edit distance. So yeah, the slides are running by themselves for some reason, but this is you clapping because you love my talk so much. I think it's a good place to stop. So thanks a lot. And if you don't know what to ask, I have some bonus slides. You can just ask to see my bonus slides.
Yeah. Okay, great. So this is very tempting. I mean, I am going to ask about bonus slides. Let's just see if somebody asks questions first. Let's see. What about communication complexity?
Great. That's a great question about communication complexity. You can ask what happens if you restrict the pre-processing to something small. I'm not sure I know a good answer.
Good. So before, I mean, I really want to see bonus slides, but again, quick question. So one approach would be essentially just try to do some kind of embedding, only maybe to map, you know, A to F of A, B to F of B, and try to compute the answer from that. I guess it's very restrictive. So I assume it's very restrictive. It will not work for your special cases, or there are low bounds. If you only like try to sketch, somehow maybe compress the strings to something smaller or something like that.
Yeah, it's a good question. Maybe I'll show you a couple of bonus slides. I'll
Let's go for bonus slides.
I'll tell you what we actually do, and then
let's go for it.
Yeah. So, but if there are any questions, feel free to interrupt while I'm showing you the bonus slides. So, how do I do this? Good, bonus slides. So first, I wanted to put our work in perspective with other work. So, our paper makes sense in the case where number of sequences is roughly up to polynomial factors, roughly the equivalent to the length of each sequence. In comparison, there's a lot of work on two very long sequences, and so no pre-processing, you just want to compute their edit distance. And we'll see the last talk by Josh will also be about this model. And there's also a lot of work on approximate nearest neighbor with edit distance metric. And there, typically, we think of the length as very short, and we have a huge number of sequences. And our model is sort of in between. Good. A completely different bonus slide. We actually have a bonus result. We improved the state of the art for no pre-processing algorithms. So if you want to do approximate edit distance with some constant factors, as Josh will tell you in the last talk, you can do that in near linear time. But if you want a reasonable factor, say 3, which is the best we know to do in subquadratic, we improve the state of the art from 1.69 to 1.6. Okay, last bonus slide. There are more, but I'll stop here. How do we actually use pre-processing? for the small edit distance algorithms, we just pre-compute hashes of every contiguous substring, every block of the substring. And then the pre-processing roughly takes linear time. For the approximate edit distance algorithm, we compute the pairwise edit distance of different blocks. That's it. Oh yeah, one more slide. So these algorithms are super simple. We promised when we submitted the paper, we promised to explain the algorithms in the fully explain the algorithm in a single STOC talk. I didn't expect to only have 5 minutes, so hopefully you get.
Oh, that's great. No, thank you, Ed. So yeah, so we'll try to, if there are more questions, to stick around at the end. But definitely look at the full longer talks. There are many more results over there. All right, thank you once again. So we will move to the third talk. So the third talk is dynamic algorithms for longest increasing subsequence and distance to monotonicity, and it will be given by Sayed.
So I hope you're hearing me well. Let me know if there's any problem. Okay, so this is a joint work with my advisor, Michael Mitsemacher.
We don't see your slides yet, Sayed. Maybe they're coming, but okay, now,
you see it now?
Yeah, go ahead.
Okay, so here's the problem definition. It's very simple. There's a sequence of numbers on the screen. We would like to find this subset, a subset of elements that is increasing. The maximum of this subset is longest increasing subsequence. And the dual of this problem is distance to monotonicity. Basically, the smallest number of elements that you have to remove such that the remainder is increasing. The algorithm for LIS and distance to monotonicity is very famous. It's called patient sorting. So we basically add the elements one by one. Every time we add one element, we do a binary search, and that's enough for updating the solution. So in the end, we can figure out what's the LIS for a sequence. This is a very simple algorithm, and it gives us a solution in time n log n. You can probably implement it in less than 10 lines. And it has also some application in other settings, such as streaming or massively parallel computation. Unfortunately, it's very bad for one setting, and that's the reason we studied this work. So in the dynamic setting, assume that you have the LIS of the sequence, and then I remove some of the elements. And I ask you to give me the LIS of the remainder. Now, the issue is that if you want to run patient sorting, you have to go all the way back to any of, before any of the changes are made. And from here on, add the rest of the elements. And again, adding every one of them takes time log n. So in total, you may need to run your algorithm for time n log n. And this is equal to computing the solution from scratch. So this doesn't give us any improvement. All right, so this is our setting. We start with an empty array. At every point in time, we either add one element, or we remove one element, or we change one of the elements. And every time we do this, we ask what is the size of LIS, or what is distance to monotonicity. Ideally, we would like to keep the exact solution, but if that's not possible, then approximate solution is also great. All right, so here is what we know for this problem. It follows from patient sorting that if everything happens at the end of the sequence, then you only need time log n for update, because patient sorting is actually doing that for us. Apart from this, there is another work that studies the problem in the setting that the changes can happen everywhere. And they give an algorithm that it gives you the exact solution, but the runtime of this algorithm depends on the size of the solution. So for instance, if the size of the solution is R, then the runtime of the algorithm is R plus log n. This is good if the size of the solution is small, but in the worst case, it could be as large as n, which gives us runtime linear. So what we do in this work is we give truly sublinear time algorithm. Regardless of the size of the solution, the runtime of algorithm is sublinear. So we begin with a simple algorithm. It gives us 1 plus epsilon in time root n. This probably, a warm-up. It's a very, very easy algorithm. If you probably think about this for a couple of hours, you'll figure out. It's a trade-off between the previous algorithm and an easy trick that loses 1 plus epsilon but improves the runtime. The main contribution we're giving is this one. We give update time n to the epsilon, and approximation factor is constant. So long as epsilon is constant, the approximation factor remains constant, but the trade-off is exponential. So it's 1 over epsilon to the 1 over epsilon. So in the end, I'll say a few words about this one. But we also have some side results. For instance, if we only add elements to the problem, we don't remove anything, then we can get log n approximation times log n cube. This is possible because when we only add elements, the solution only increases, it never decreases. And because of that, we can design a better algorithm. We also have a solution for DTM. It's n minus LIS. So it seems that it should be similar to LIS, but actually it's not. It's much easier. So we can get 1 plus epsilon approximation in time log n squared. It's the update time. And this is much better than the solution we are giving for LIS because distance to 120 is actually a simpler question. So if you consider other settings such as streaming or MPC or the classic sequential setting, the solutions we know are much better for LIS. So I don't have time to explain the technicalities. I can tell you how we get the main solution. So the technique we are introducing is called grid packing. It has some connection to recent developments for edit distance. So one step of the algorithms you're giving for edit distance is, we call it window compatible solutions. In order to approximate the edit distance of 2 strings, we divide the problem into smaller subproblems. And we claim that if we know the answer to these smaller subproblems, we can figure out the answer for the actual input. So we do the same thing for LIS. The construction is different, but we divide the sequence into smaller pieces. We call them segments. And we promise that if the solution for every segment is available, based on that information, we can get constant approximation for the LIS of the whole sequence. Now, how does that help us? Because suppose something changes, we only need to update the solution for the segments that cover that element. Because the size of every segment is small, then we can update the solution for those segments in sublinear time. In addition to this, we prove that the number of segments that cover every element is small. So if we multiply that runtime by the amount of segments, it's going to still be sublinear. So that's a very short explanation of the sublinear time algorithm. How do we improve the runtime to n to the epsilon? We recurse on the same idea. So instead of computing the solution for each segment separately, we run the same algorithm. So inside every segment, we again construct segments and use the same idea to compute the value. So if you repeat this procedure 1 over epsilon times, then the update time reduces to n to the epsilon, and the approximation factor would be 1 over epsilon to the 1 over epsilon. All right, so that's roughly what we are doing. If you're more interested, I have a longer version that explains everything in more detail. A few questions that seem very interesting here are whether we can get exact algorithm in sublinear time. All of the results we are giving are 1 plus epsilon or constant approximation, and we don't know any sublinear time algorithm for LIS. And of course, there's a question of lower bound. The only lower bound that I can think of is log n, because LIS needs time n log n. So in every operation, we need to at least spend time log n. But the gap is wide open. So the upper bound is n, the lower bound is log n. Any improvement would be very interesting. So that's it. If there's any questions, I can answer.
Great. Well, thank you. So, okay, there is a quick question. Is the update time amortized? If
No,
not, would it help? It's worst case. And it wouldn't help, yes, as far as you can see. I see. And your algorithm is comparison based, right? You don't look at the numbers, like it's actually a representation of the numbers. Is it?
Well, no, it's not compared. Yeah, we look at the numbers.
I see.
If we don't know the value, then at least I don't know any easy way to implement the same algorithm.
Oh, so you use more like for basic LAS, then log algorithm is just compares numbers. It's a comparison-based algorithm. You actually need to know the numbers,
yes,
you know, the representation of numbers. I see.
So our algorithm needs to know, but probably there is a way to get around that. I haven't thought about it, but that's an interesting question.
I mean, do you know anything about additive? Right, because for DTM it shows it looks like the same problem, but for multiplicative, of course, version it's not the same. For additive, it would be the same. Do you know any additive guarantee if you want to approximate LAS within like additive delta?
So if probably the question is easier if you want to get additive error delta times n, where delta is constant.
Okay.
But for a smaller delta, I haven't seen any work that considers that.
Well, could be an interesting thing to consider. Just
yeah,
yeah. All right, great. So if there are no more questions, I guess we are right on time. So then let's move. But yeah, if you have more questions, feel free to answer. We'll stick around a little bit afterwards. Let's move to the last talk of the session. It's a merger of two very related papers. Constant factor approximation of near linear eddy distance in near linear time, and constant factor approximations to eddy distance on far input pairs in near linear time. And Joshua, the author of the first paper, will give a talk.
Hello, I'm Josh. Welcome to the talk. Thank you for the introduction. So yeah, this is joint work with Michal, or this is joint work with Aviad, and then another paper by Michal and Mike. Okay. I guess we can do this part quickly since this is the, there's already been a few talks on it, but the edit distance between two strings is the number of insertions, deletions, and substitutions needed to go from one string to another. There's a classic n-squared dynamic programming algorithm which solves this exactly. And assuming the strong exponential time hypothesis, you can't hope for a substantial improvement in this algorithm, which has led to the community having an active study of approximation algorithms, which I'll go over in the next slide. So to show all the different work on the approximate edit distance problem, I'll have the x-axis show the approximation factor and the y-axis show the time. So for instance, the classic DP algorithm is in the upper left corner. And then there's a linear time square root of n approximation algorithm due to folklore. This was steadily improved to a sublinear approximation, a sub-polynomial approximation in linear time, a polylogarithmic approximation in near linear time. And then most recently, there's been last few years, a breakthrough in getting constant factor approximation of edit distance in subquadratic time. So first a quantum edit distance, a quantum algorithm by VGHS, then another classical algorithm by CDGKS. And then, as was mentioned in Aviad's talk, there's been a few other algorithms that are now improved the constants, but all of these constants are at least n to the 1.5. The main contribution of this two papers is a near linear time algorithm that gives a constant factor approximation with a caveat that it only applies to large edit distance, or in other words, there's also an additive error of n to the 1 minus some epsilon prime. Okay. So to state this result formally, for every epsilon, there exists a delta such that you can approximate edit distance in time n to the 1 plus epsilon to a multiplicative factor of 1 over delta and an additive error of n to the 1 minus delta. As a corollary of this, earlier this year, Aviad and Jiao showed a reduction from LCS to edit distance, and as a corollary, we using our algorithm, sorry, large distance LCS, then you can get a 1/2 plus delta approximate binary LCS in n to the 1 plus epsilon time. Very recently, there's been a breakthrough by Andoni and No Satsuki, which dropped the additive error entirely. So they get an n to the 1 plus epsilon time algorithm with a 1/delta approximation. So there's no additive error. And in particular, it supersedes our work. But a number of the ideas in our algorithms also appear in the Andoni No Satsuki algorithm. So understanding both can be useful. Okay, and taking a step back at just the landscape of results on approximate edit distance, a giant gap right now is trying to figure out a 1 plus epsilon time approximation factor for edit distance and subquadratic time. And this is actually so all the recent breakthroughs which give constant factor approximations, none of them are able to get this 1 plus epsilon approximation because they crucially use a triangle inequality trick introduced by BGHS, which requires the approximation to be at least 3. Okay. So there's very little time, but let me just very briefly say what the algorithm looks like. The first few steps build off of previous work. So what we would do is we'd take our string and we'd break them up into a number of chunks called windows. And we would like to be able to estimate the edit distance between pairs of windows. And to do this, you're essentially doing a graph, sort of a graph search problem, where if you think of trying to discover a graph where edges are pairs of windows that are close together. BEGHS was able to do the case where the graph is dense to get a subquadratic algorithm and then used Grover search otherwise. CDGKS was able to give a classical algorithm in the sparse case, which was enough to get a subquadratic algorithm. And what our papers do is sort of combine both of the approaches recursively in order to get a near linear time algorithm. If you'd like to see more details, you can watch the longer talk on YouTube or read the papers. Just to recap, we know that classically you're unlikely to solve edit distance in subquadratic time, but large constant approximations can be found quickly. Thank you.
Great, thanks, Josh. So let's see if there are any questions online. Let's see if there are any raised hands. Well, I guess feel free to type questions. So one question, so how bad is this delta as a function of epsilon?
The delta is approximately double exponential in epsilon.
I see. In all the papers, so in some papers better than others?
So
like 3 papers.
In both of our papers, it's roughly double exponential. I'm not sure. I think in Andoni No Satsuki is either double or triple exponential. I'm not sure.
Oh, I see. It could be even worse. Okay. Is there is a conditional hardness or some kind of result that this dependence between epsilon and delta is inherent? Double exponential, even any low bounds?
No, we're not aware of any lower bounds. I mean, I guess it's not even clear. I mean, we don't even know that there isn't a 1 plus epsilon near linear time algorithm.
And the smallest constant, well, I guess none of your constants will even approach 3, right? Even if even if you want just a little bit subquadratic. So if epsilon is basically 1, in your case, is your constant approaching 3, or it's just much worse than even if epsilon equals
I guess
1?
You could make it I guess if you're having your constant approach 1, then, well, I guess if you want epsilon is going to be like 1 over some integer, or roughly. It's formally stated that way in KS, slightly different in my paper with Fabiat, but it would, so basically epsilon equal 1 would be like would be just the traditional dynamic programming, and then epsilon equal 1/2 would be like similar to these other algorithms. Although, yeah, we didn't try to optimize the constants.
Great. So let's see if there are any more questions. We do have a minute to go. Let's see. So I guess we can take the time. So let's see, almost everything I believe was answered. So there is this question about dynamic time wrapping. And there was one more question, I think, very briefly to, I guess, Said. Yeah, it was a question about the sublinear time result to Shai. Namely, can he very quickly, I guess, explain the sublinear result? But if it's very quick, we'll take this question and then we'll stop the recording.
Yeah, just Said asked it in the chat. He asked how we output the solution in the sublinear time algorithm, and I respond in the chat that we just report the positions where there is an occurrence of the pattern, and we assume, I mean, the algorithm is sublinear in the case that the number of positions where the pattern appears with at most k mismatches is sublinear, which is the common case, of course.
Okay, great. All right, so we can stop the recording. Thank you all the speakers for great talks. And if there are no more raised hands, if anybody wants to answer a live question, feel free to speak up, I guess.